Hello everyone, welcome you in my YouTube channel. I am Dr. Mohammad Sirajul Fazi, Assistant Professor, Department of Chemistry, Hills College, Muzaffarpur. Today in this video I am going to explain about crystal, single crystal X-ray diffractions. So let us start with the basic unit cell, the building block of crystalline solid. What is the properties of unit cell? The parameters that define the unit cell are A, B, C, unit cell dimensions along X, Y, Z respectively, and alpha, beta, gamma, angles between BC alpha, AC beta and AB gamma. So this is one unit cell, this is one unit cell. A unit cell is defined by ABCD, ABC and alpha, beta, gamma. Now, shapes of unit cell. All possible shapes of unit cell are defined by 7 crystal system, which are based on the translations relationship among ABC and alpha, beta, gamma. You see, A is equal to B is equal to C, alpha is equal to beta is equal to gamma is equal to 90 degree cubic system. A is equal to B, B is not equal to C, alpha is equal to beta is equal to gamma is equal to 90 degree tetragonal system. A is not equal to B is not equal to C, alpha is equal to beta is equal to gamma 90 degree orthorhombic system. A is equal to B is equal to C, alpha is equal to beta is equal to gamma is not equal to 90 degree rhombohedral. A is equal to B is not equal to C, alpha is equal to beta is equal to gamma, beta is equal to 90 degree, gamma is equal to 120 degree hexagonal system. A is not equal to B is not equal to C, alpha is equal to gamma is equal to 90 degree is not equal to beta monoclinic system. A is not equal to B, B is not equal to C, alpha is not equal to beta, beta is not equal to gamma, gamma is not equal to 90 degree. So all side and all angles are not equal. Triclinic system. So 1, 2, 3, 4, 5, 6, 7 system. Now crystalline materials are characterized by the orderly periodic arrangement of atoms. You see, there is a order of arrangement. The 200 plane of atoms in sodium chloride and the 220 planes of atom in sodium chloride. So this 200 and then 220. The unit cell is the basic repeating unit that define the crystals. That is very basic. Parallel planes of the atoms intersecting the unit cell are used to define the directions and distance in the crystals. So these crystallographic planes are identified by Miller indices, means HKL. So atoms in the crystals are a periodic array of coherent scatters and thus can diffract X-rays. Diffraction occurs when each object in a periodic array is scattered readily, coherently, producing concerted constructive interference at specific angles. The electrons in an atom coherently scatter X-rays. The electrons interact with the oscillating electric field of the X-ray. Atoms in the crystal form a periodic array of coherent scatter. The wavelength of X-rays are similar to the distance between atoms. So friend, diffractions from different planes of the atom produces a different diffractions pattern which contains information about the atomic arrangement within the crystal. So these are important points. Focus on this point. X-ray are also reflected, scattered incoherently, absorbed, refracted and transmitted when they interact with the matter. Now look at this figure, a scattering of X-ray by crystallographic planes. We need to consider how X-rays are diffracted by parallel crystallographic plane. So this is, you have a lattice plane, this is one lattice plane, another lattice plane, at the distance d, incident rays, diffracted X-rays, incident X-rays, diffracted X-rays. So atoms on the lattice plane. X-ray diffracted in phase will give you a signal. In phase means that peak of one wave matches the peak of the following. This, if it is matches, then it is give the signal. Diffraction occurs only when the distance traveled by the parallel X-ray are an integer of the wavelength. You see, this is theta angles, this A, B, this is the distance D. The diagram shows only two scattering plane, but implicit here is the presence of many parallel identical plane, each of which is separated from its adjacent neighbor by spacing d. Constructive interference, a diffraction occurs when A plus B divided by lambda is equal to n. The integers n refer to the order of diffraction. For n1 n is equal to 1, A plus B is equal to lambda, and n is equal to 2, A plus B is equal to 2 lambda. So you can see this is the Bragg diagram. The angles of incident theta, the angle at which the X-rays are diffracted is equal to the angle of incident theta. This is theta. The angle of diffraction is the sum of these two angles. This theta become 2 theta. The two X-ray beam travel at different distances. This difference is related to the distance between parallel plane. We connect the two beams with perpendicular lines CD and CF. This is CD and CF. CE interplanar distance, CE interplanar distance gives two equivalent right angles. So sin theta is equal to d by d. Here is d e by d. D sin theta is equal to d. D is equal to ef. D sin theta is equal to ef. So 2d sin theta is equal to ef plus d. Ef plus d. Distance travelled by the bottom wave. So this condition is met when the distance equal an integers multiple of the wavelength, called order of diffractions n. The final equations is the Bragg's law, n lambda is equal to 2d sin theta. Data are collected by using X-ray of known wavelength. The sample is rotated at angles of diffraction changes. When the angle is corrected for diffractions, a signal is recorded. You see, with the modern X-ray diffractometer, the signal are converted into peaks. This is the peak. This x-axis is 2d, 2 theta degree, and y-axis intensity. Here small one 200, 110, 400, 310. This is the scale value. So friend, Bragg's law is a simplistic model for understanding what conditions are required for diffraction. Lambda is equal to 2d HKL sin theta, or d HKL is equal to lambda by 2 sin theta. So parallel plane, you see the distance of atom with a space DHKL between the planes. Constructive interference only occurs when the Bragg is satisfied. In our diffractometer, X-ray wavelength lambda is fixed. Consequently, a family of plane produces diffraction peak only at a specific angle theta. Additionally, the plane normal must be parallel to the diffraction vector. Plane normal, the directions perpendicular to the plane of the atoms, and diffraction vector, the vector that bisect the angles between the incident and diffraction beam. The space between diffracting planes of the atom determine the peak positions. The peak intensity is determined by what atom are in the diffracting planes. The atom, a molecular distance in angstrom, and wavelength for the diffraction lambda is approx 1 angstrom. So friend, hope this video will be helpful to you. If you like this video, then subscribe my channel. Thanks for watching.